All right, so today we're going to talk about something you've never heard of before, probably, called residuals. A residual is the difference between what actually occurred versus what we predicted would occur based on a best fit model, like when we make a scatter plot with a fitted line and we say, oh, this is what should happen versus what actually happens. So Battle Creek cereal is trying a variety of packaging sizes for their Crispy Puffs cereal. Below is a list of data for 6 current packages. Write a sentence or two to the executives of Battle Creek cereal describing the association. So we're saying, 34 square inches is used to package 21 grams of cereal. 150 square inches is used to package 198 grams of cereal. So what we're noticing is as the packaging increases, the weight of the cereal inside is increasing as well. So amount of packaging increases, the net weight also increases. That makes it a positive association or positive slope. Now, I wrote moderately strong with no outliers. And in order to know that, you would need to create a scatter plot. So attached, you have a blank scatter plot. And what I did was I filled mine in so that you could see sort of what I was predicting. And I had packaging along the bottom. That was already there. Weight in grams, I counted each square to be worth 100. I did need one that was way down here at 34, and then I needed another one up here at 1,020. So it was the best that I could do to keep my data as spread out as possible. If you counted by, say, 200s, or if you counted by, say, 75 instead of 100, it would have fit that last dot on the grid as another option as well. So moderate association. Now, the reason I said that is because the dots you can see are definitely in a linear pattern, but they're not perfect. You've got one over here, one here, one here, one here, another one kind of up above. So I do have 3 dots above my line, 3 dots below my line, but they're not lined up the way they were for section 411 on that assignment when we did a scatter plot. So moderate because they are linear, but they're not like, oh, look at that line. They're a little bit more spread out. And I don't see any outliers. I don't see any points that are so far away from my fitted line that they're causing a problem. I didn't have any dots that were so far away that it was really pulling my line in one direction or another. All right. So first thing I did was create the scatter plot. Give an equation the executives can use to predict the net weight of cereal based on the amount of cardboard. So I used the points 200, 300, and 400, 800. And you'll notice that those are in yellow because those are points on my fitted line, but they were not in the original data set. So if your fitted line is different than my fitted line, then the 2 points that you choose would be different. So I did y2 minus y1 over x2 minus x1, and I found that my slope was approximately 2.5. I then used the point 200, 300 to find that my y-intercept was going to be negative 200. And if you look at my graph, it definitely looks like this line is going to be down here in the negatives, and 200 seems like a reasonable distance below 0. All right, so I am going to be using, for my fitted line, the equation y equals 2.5x minus 200. Tell the executives how much cereal a new experimental green package that uses 260 square inches of cardboard is expected to hold. So what we would do is we would use our new equation, which was y equals 2.5x minus 200, and then we plug in 260 as our x value. Because if you remember on the graph, the x-axis had packaging. So we plug in 260 as our x value. 2.5 times 260 is 650, take away 200, and we get 450. So we would predict that if it's going to use 260 square inches of cardboard, that would hold 450 grams of cereal. If we look on here, 260 looks like it is between 400 and 500, and this one's predicting 450, so we're in the right area. Interpret the meaning of the slope and the y-intercept of your model. So slope is rise over run. So if you look at my graph here, I wrote it off to the side. Slope is rise over run. The rise on the y-axis was weight, and the run on the x-axis was packaging. So it's grams per inches squared. So the slope is saying, in this case, we had 2.5. So for every 2.5 rise over run, so 2.5 is your rise, that's your y-intercept. For every 2.5 2.5 grams of cereal, we will need 1 square inch of packaging. And I've got that because the slope is 2.5 or 2.5 over 1. So that's 2.5 grams for every 1 square inch. That's my rise over my run. Or you can say it's your y-axis over your x-axis. So the slope is 2.5. For every 2.5 grams on the y-axis, we would need 1 square inch from the x-axis. That's our slope. And then the y-intercept is a little easier, b. In this case, it doesn't apply. There are certain restrictions where we can't always extend something on forever. It doesn't work forever. So in this case, we would say b is a negative amount of cereal. So it does not apply to negative numbers. It just doesn't extend that far down. So does the y-intercept make sense in this context? Why or why not? No, for a couple reasons. One, not all models are perfect. And I didn't know that was going to happen. It's just a matter of your fitted line, how low it goes or not. Not all models are perfect or can be extended forever. And that applies to both directions. You may not be able to extend this model forever up to the right either. Okay. A residual is the measure of how far a prediction is from what was actually observed. So in order to get the residual, we will always take the actual value and subtract the predicted value. In the 260 square inch box from problem 410, it will actually hold 455 grams of cereal. So this is our actual. And from the front, we noticed that the predicted was, we said we predicted it was going to hold 450. So what we need to do is look at the difference between the actual and we would subtract the predicted. The actual holds 355 grams. We would take away the predicted 450 grams and we would get negative 95 grams. Now, what does that look like on our graph? So if I look here and we are looking for an X of 260, 250, 260, and we're looking for like where it hits on the line, we predicted that it was going to be 260, 450, and that would be on the fitted line. But the actual 260 was more like 355 down here. And what we would be doing is we're measuring this distance from the predicted to the actual. So this one is predicted by the fitted line, and this one is the actual. And we're just finding the distance. How far away are those two dots from each other? So on here, we found that one dot was 95 grams off. What does it look like on the scatter plot? It is a vertical segment directly below or above, because it might have been higher, this case was lower, directly below or above, below or above a point on the fitted line. So we're saying how far away is the actual value from the predicted value on the fitted line? What's the difference between a positive and a negative residual? Now, if we look at this specific example, we thought it was going to hold 450. It actually held only 355, and we got a negative answer. So negative residuals means the box holds less than predicted. We thought it was going to hold 450. It only held 355. So that is negative. How could graphing the actual and predicted data points help? Well, one thing that we do is we really should have the same number of positive residuals as negative residuals. That's the reason that we try to split our points down the middle when we're doing the fitted line. So here we've got a positive residual. This box held more than we predicted. Here we've got a negative residual. This box held less than we predicted. Another negative residual because it held less. Another negative because it held less. This one held slightly more, and this one, if you extended the yellow line, would actually hold a lot more than predicted, because remember, this line ends up extending down into the negatives. So we should have a matching number of negative residuals with the number of positive residuals. So how could graphing the actual and predicted data points help? We should find that we have the same number of negative and positive residuals. What is the residual for the 471 square inch box? So we need our equation first, and our equation, there we go, there's a pen. Our equation was y equals 2.5. We're going to plug in 471 because that's the inches squared. That's the amount of packaging minus 200. And we're finding out how much do we predict that is going to hold. So 2.5 times 471 is 1,177.5. Take away 200, and it's 977.5 as our predicted number of grams. So let's go back to the graph. The 471 is this point up here, right? So we're going to say here it is on the line. On the fitted line, we went 471 and we got 977.5. The actual point up here was 471.1020. So in this case, that point is above the line. It's going to have a positive residual. So we would do 1,020, take away the 977.5, and it has a positive 42.5 gram residual. Now, you don't need the plus sign there, but I'm putting it there because I'm saying it at the same time to say this box held 42.5 grams more than our fitted line would have predicted. The warehouse store wants to offer a supersized 600 square inch box. The residual for this box is 1,005 grams. What is the actual weight? So if the residual is 1,005, what we're saying is it's holding 1,005 more than predicted. So we would want to use the equation y equals 2.5 and then plug in the 600. And we'd have to do 2.5 times 600, which would be 12, 13, 14, 1,500 minus 200, giving us y equals 1,300. Let me double check that. I think on my original, I had different numbers, so it's coming up slightly different. 2.5 times 600 is 1,500, take away 200 is 1,300 grams. So we are predicting that it'll hold 1,300 grams, but the residual came in at a positive 1,005. It ended up holding 1,005 more grams than we predicted. So we would add those together. We would say, okay, we thought it was going to hold 1,300, but a positive 1,005 residual means the actual weight is 2,305 grams. Why do you suppose the residual is so large? Well, remember how at the bottom of the graph we said it wasn't very reliable. It went down into the negatives. You can't always continue things forever. The same thing holds true when you go too far away in the other direction. We don't know if the graph will continue to be linear. Will it start to follow a curve? When you get too far away from the data you've collected, you can't know how reliable it will be. So the graph may not continue to follow the same pattern. forever. And this really goes back to what we said on the front. Like, it may be valid in a small segment, but not continue to be true for very, very small or very, very large numbers. Armin was concerned about the amount of sugar in his diet, so he went to the store and collected data from several cereal boxes. Armin used the data to create a model that related the amount of sugar in cereal to the number of calories. All right, so we've got an equation, S equals negative 16.9 plus 0.23 C, where S is the amount of sugar in grams and C is the number of calories, okay? What does a negative residual mean in this context? So for this question, if you had something that came up with a negative residual, it means that the amount of sugar is less than what was predicted by the model. So the sugar is less than predicted. That would be a good thing for Armin because he wants to watch how much sugar he's taking in. So if he had a graph, he'd want to pick all of the types of cereals that had points below the fitted line, because those points below the fitted line would have a negative residual. Negative residual would have less sugar than predicted. That would be a good thing for him. So is the cereal with positive or negative residuals good for his diet? He wants the negative residuals. Interpret the meaning of the slope and y-intercept in the context of the problem. So the slope is your 0.23. So for every 0.23 grams of sugar, the calories increase by 1, right? Because it's 2.3 over 1. So you're saying grams of sugar go up by 2.3 for every 1. And is everything measured in grams? I believe it was. It would be for every 1 calorie. All right, so 0.23 grams of sugar for every 1 calorie. All right, and then y-intercept. The y-intercept is negative 16.9 grams, which again, we would say doesn't apply. In this case, we're saying that this data cannot extend into the negatives. It doesn't make any sense. So the y-intercept is there because it's part of the pattern, but it does not make sense to use that number for any practical reason. So does the y-intercept make sense in context of this problem? No. And that's okay, because we wouldn't eat 0 calories of cereal and expect it to have negative 16.9 grams of sugar. That just doesn't make a lot of sense. So that's okay. That happens. We have plenty of graphs out there where the y-intercept is not exactly what we thought it would be. Just like yesterday's, the 4.1.1, where we thought that the width of the tube would be our y-intercept and they were slightly off. Same idea. We would expect that 0 calories of cereal would have 0 grams of sugar, but the models don't always work out perfectly because at some point they might curve, at some point they just might not be accurate anymore, and that is the case here. So I'm sure we will have lots of questions about residuals, which is totally fine. Go back to the beginning of that back side of the page. That's really what matters here. A residual is the difference between the actual amount subtracting the predicted amount. What's the difference? Did we end up with a predicted amount and an actual amount that were really close, or were they really different? And that number is your residual. How far off? All right, I will talk to you in class. Bye.